Okay, so let's have our second problem of a first order homogeneous differential equation. So we've got x squared dy dx equals y squared plus xy. Let's check if this is indeed of the criteria of homogeneous. Look, this is x squared, so it's of degree 2. Let's look at this term, it's of degree 2. This is xy. So x is degree 1, y is degree 1. So the term xy is actually degree 2. So you can see that all terms have the same degree, and this equation, this equation is first order homogeneous. Okay, now let's go ahead and solve this. Before we can do that, remember, for such equations, we make use of the substitution y equals ux. Of course, this means u equals y over x. Sorry, u equals y divided by x. So let's first rearrange the terms here to make sure we've got y over x at certain points. I'm going to divide this equation by x squared. That will create some y over x terms. So if I divide by x squared, so let's go ahead and do that. Divide by x squared, the equation is going to become dy over dx equals y squared over x squared plus, that's y over x. Okay, this is good because now we have y over x at certain points, and we are going to substitute that with u. I'll write this better. Dy dx equals, so y squared over x squared, I'll write that as y over x squared plus y over x. So I know y over x is u, but I don't know what dy dx is. So let's go ahead and find that. From here, well, we can find what dy dx is. So let's go ahead and do that. Dy over dx equals, let's use product rule here. If we keep u as a constant, the derivative of x is 1 with respect to x. So if we keep x as a constant, the derivative of u with respect to x, there we go, du dx. Remember, u is a function of x, so we shouldn't treat u as a constant. Let's substitute for dy dx and y over x here. So that's going to be u plus x dy over dx equals, where there is this y over x, that's going to be u squared, and then y over x is going to be u. So u subtracts with u. Let's see what we have now. X, did I get this wrong? This is u du dx, not dy dx. Sorry about that. So that's x du dx equals u squared. Now you can see that this is a simpler equation that can be solved by separating variables, and that's the beauty of this method of substituting. It helps us to convert a rather complicated equation into an equation that we can solve by separating variables, or something that is exact. So let's separate variables here. We'll have du divided by u squared equals 1 over x times dx. Now I'm going to extend this a little further here. So let's see what we have in this case. If we separate this, so if we apply integrals to both sides, integral, I like to write this as 1 over u squared du, and then we have integral of 1 over x dx. So what's the integral of 1 over u squared? That's negative 1 over u. The integral of 1 over x with respect to x, that's natural log of x plus some constant c, which I like to write as maybe natural log of a. A is also another constant in this case, so I have negative 1 over u equals natural log of ax. Okay, that makes sense. If I make this natural log of a, so according to the properties of logarithms, I multiply a and x. So here we go. But we know what u is. Okay, u is actually y over x, so I put that back there, so I'll have negative x over y equals natural log of ax. Let's make y the subject of the formula. That's going to be negative x divided by natural log of ax, and there we have it, our general solution to the differential equation. Oops. So there we have our general solution to the differential equation. Okay, so check in the description and find a link to the next video where I solve another problem still about first order homogeneous differential equation.